Hello students, welcome in the part 7 of D and F local elements. In the last part 6, I gave you one question: H, I, J, K, L, M and O. Which compound I am referring? So the answer is H2O. I am referring about the water. What I said? H, I, J, K, L, M and O. It means I read from H to O, all the alphabets from H to O. H2O. Clear? Okay. Before we proceed further, let me show you some physical occurrence, in what form they are found in nature, the different crystal form, different lattice structure of transition metals. Now here you see 3D, 4D and 5D series, scandium, HCP and BCC both. Now in these, some of the elements, they are found in only one state, and some of like vanadium, chromium, BCC and some other, they are found in 2 or 3 states. It means their lattice structures, their unit cells, maybe 2 or 3 forms may be there. You see here lanthanum, CCP, HCP, PCP, all the 3 states. Now here is very interesting zinc, as we discussed in solid state as well, that zinc is having HCP structure. Now here it is where there is X and X. This X indicates typical metallic structure. Metals are what? Cations submerged in the sea of electrons. So where there is X, it means typical metallic structure is also there. Very interesting, Hg, mercury. No such any solid state geometry like CCP, HCP, BCC like that. Only X means typical metallic structure, that is cation submerged in the sea of electron. So you can see the various lattice structure of different transition metals. Okay, now let's move to the ongoing part in physical properties. Now see, the next part is melting and boiling point. Okay, so in this melting and boiling point, you see there is no regular trend. If you see, there is one graph is also shown here. Here it is on y-axis melting point, on z-axis it is atomic number. You see in the middle, somewhere in the middle, highest, somewhere in the middle you see highest melting point. Here tungsten, then molybdenum. After that in technetium it is decreased, then further rubidium again increase. Then in the third series, that is first series, titanium, you see chromium is having highest. Then as per this expectation, manganese should be like there, somewhere there, but unexpectedly manganese has low melting point. Now see this trend, why it is there, we will discuss about this. And this trend is also somewhat similar, you can say, the trend of atomized enthalpy. Atomized enthalpy, as I told you earlier, that the enthalpy change when a substance is completely separate out in all of its atoms. During that process, the enthalpy change, that is atomization enthalpy. Now see again here, higher somewhere in the middle. Then you see here, this point should be here, there, but again the trend is broken, and here again in this series the trend is broken. This green is 3D series, 4D series and 5D series. So this is the trend in the atomization enthalpy is similar to that is of melting point. So These melting point trends, they all depend on atomization enthalpy, and atomization enthalpy further depend on some other factors. So you see what the trends are there in melting point and boiling point. The first point is melting and boiling point d block elements. Melting and boiling point of d block elements are higher than S block elements. If you compare one by one, then D block elements having high melting point and boiling point than S block elements. Okay, now what is the reason for that? Okay, so reason being, if you give the reason of this, so reason being stronger metallic bonding. Now melting point directly depend on the metallic bonding, types of bonding, and metallic bonding in fact is affected by the enthalpy of atomization. So we can say stronger metallic bonding. Now why the metallic bonding in D block elements are stronger than S block? So there is the involvement of the electrons. Okay, and this is due to stronger metallic bonding as well as covalent bonding. As I discussed earlier, they also have covalent bonding unlike the S block metals. So strong metallic bonding as well as covalent bonding in transition metals. Okay, and this is due to the reason for the strong metallic and covalent bonding is unpaired electron of D subcell. More the unpaired electron, and stronger is the metallic bonding and higher the melting and boiling point. So this is the first point of melting and boiling point here. Next, if you see zinc, Hg and cadmium, as there is no unpaired electron, in D subcells. If you see zinc, Hg and cadmium, they contain 3d10, 4d10 and 5d10 like that. Now d10 configuration is there, so there is no unpaired electron in the D subcells. It means only the electrons of the S subcell participate in the bonding, and as a result of that, no covalent bonding. Okay, no covalent bonding. If bonding becomes weak, then we can say they are having low melting point as well as boiling point. That's why they are known as volatile metals. They are known as volatile metals among the D block elements. That's why mercury is found in the liquid state.